So Pappus was this Greek dude who lived long before calculus was discovered. But he had this notion that if you had a region and you could calculate the area of that region, and then you have an axis, let's say, that you want to rotate that region around to generate some sort of thing. I always draw a region that I find impossible to reflect. Anyway, so this whole thing is supposed to rotate around. The region stays the same as you do it. So you're making like a donut or a bagel or a torus, right? He says, if I can calculate the area, I ought to be able to calculate that volume just by taking the area times some length, right? I mean, that's what volume is. You calculate an area and you integrate it over a length, so you get volume times length. The question is, what length? Because if you multiplied it by the length going around the inside here, well, that might be too small. Or take the farthest point away, and you multiply it by that length going all the way around. That might be too big. So maybe there's a point in the middle that you could figure out its distance. So we're going to say the volume is equal to the area of this region times 2 pi times some radius, because 2 pi times a radius is going to be the distance all the way around. So we're going to find, let's do this in red here. Let's find, some point here that, call that r, so that the distance going all the way around that circle, all the way around that axis that we're rotating, would be 2 pi times r, and that would be just the right length to multiply by the area in order to get the volume. Well, it turns out that this r value, the point that you need here is you need the centroid, figure out where the centroid is, and figure out how far the centroid is from the axis. So r is the distance from the centroid to the axis of rotation. Let's do an example. Let's take my favorite region. Let's take this y equals x and y equals x squared. Whoops. I'm a little overzealous here. Y equals x squared. And let's rotate it around, actually, the line y equals x. Let's rotate it around that diagonal line. So that's going to rotate like this. Going to kind of make this football thing, right? Or rugby ball or whatever. It's weird because the angle here is 90 degrees, but the angle up here is less than 90 degrees, so it's not symmetric that way. I picked this region for many reasons. One is because it's my favorite region, but I also know where the centroid is, right? The centroid is at, so x bar, y bar is, we calculated this to be 1/2, comma, 2/5. Right? So the question now is, how far away is that point from this axis? So I'm going to zoom in a little bit here. So I've got this point here at 1/2, comma, 2/5. 2/5 is actually a fraction, not 25. 2/5. And I want to know perpendicular distance up to there. How far is it? Now, there's many ways that people calculate this. I am going to do it by, I haven't even decided yet. I could do it by calculus, I could do it by some linear algebra, I could do it by just basic algebra, finding equations of lines and finding the point of intersection. Well, I'm going to do it by calculus. So you may want to, I'm going to go through this fast, you may want to pause the video so you can look at things. But anyway, I'm going to call the distance r. And take any point on here, on the line. So this is the point xy, but because it's actually on the line y equals x, this is actually the point xx. Anyway, the distance squared is x minus 1/2 squared plus y minus 2/5 squared. So the difference between the x values here and the y values there, and then add them up, square them. Or square them and add them up, and then take the square root. But don't take the square root because I want the radius squared. I'm going to replace the y by x to force myself to be on the line y equals x. And so here's my formula for r squared. Here's the derivative with respect to x. I can maximize or minimize in this case, when the derivative is equal to 0. So I set this equal to 0, solve for x, and x turns out to be 9/20. Since I'm on the line, that's this point right here, since I'm on the line, the x and the y coordinates have to be the same. Now I plug that back in and find that the distance is the square root of this plus that, which is this, which turns out to be 2/20. Sorry, radical 2/20, which is the same as 1/10 radical 2. And as soon as I saw that, I thought, dang, there's probably a lot easier way to do this. In particular, if this is my centroid, I know that the y-coordinate was y/2, the x-coordinate was a half. So if I go straight up till I hit that line, then I'll have both the x and the y-coordinates being a half right there. And in particular, that diagonal length, or that vertical length, is the difference in the y values. So a half minus 2/5 is 1/10. So this is 1/10, but I see that as the hypotenuse of a right triangle right here. So I can just divide by the square root of 2 to get this side right here. So 1/10 divided by the square root of 2. Anyway, that's what the radius is. So what did we do? At some point in our history, we have calculated that the area of that region, so here we go now, let's come back here. Actually, I've done this several times now. The area of this region here, right, the area equals 1/6. I just calculated that the r value there, that little r, I don't know if you can see that, but the distance from the centroid to the axis there is equal to 1/10 radical 2. So if I rotate around that line to generate this region, the volume by the Pappus is 2 pi times this radius times the area, for a grand total of, let's see, it's going to cancel the 2 and the 10 cancel to leave, or let's say cancel that to leave a 3, so 30 radical 2 on the bottom, pi over 30 radical 2. And pi over 30 radical 2 is a pretty small number. It's equal to 0.074 and some change here. So pretty small volume, but it's a pretty small region. And it's being rotated around an axis very close to it. So anyway, the theorem of Pappus allows us to calculate volumes of revolution around when you rotate around any axis. You got to find the centroid. You got to find how far away the centroid is from your axis, and you got to find the area of the region. The area of the region times 2 pi times the radius, that distance from the centroid to the axis. That product equals the volume of this thing. Now, I want to take a look at how this relates, because suddenly I've got centroids and volumes of revolution being tied together, and I already noticed a relationship. So let's cement that in here. Let's say I've got a region here bounded on the top by y equals f of x, bounded on the bottom by y equals g of x. And let's rotate from a to b here, from a to b, and let's rotate this around the x-axis. Okay. So when you find the centroid here, the centroid is x bar, y bar, right? The distance from the centroid to the axis, we're calling that r. Well, that's a vertical distance. That's just y bar. So in this case, y bar is r. And y bar is calculated as 1/2 the integral from from a to b of f of x squared plus minus g of x squared, right? Dx. Actually, yes, that is, but I don't even want to do that. I'm going to just say it's equal to y bar. We're going to erase this. I'm not going to erase it in the video because you saw me do it. It's y bar. I have another way of calculating y bar because look, the volume of this thing, the volume is supposed to be, right? We're doing this by the washer method. So this looks like this, and you get like that, and all these washers in here. Each little rectangle gets rotated around to generate a washer. And the volume is the integral from a to b of pi times the outside radius squared minus the inside radius squared dx times dx. But Pappus says the volume should be 2 pi times the radius r, which is y bar, times the area. Well, y bar, remember, was mx divided by the area. So this is 2 pi mx divided by the area times the area. So the volume is 2 pi times mx. That's what we noticed. Right? Likewise, if I take that same region bounded above by y equals f of x and bounded below by y equals g of x, and now, between a and b, and now we're going to rotate it around the y-axis to do the shell method thing, right? The centroid is here at x bar, y bar, x bar, comma, y bar. The axis is the y-axis, so in this problem, r is measured this way. Come on now. R is measured this way. Well, that's the distance from the centroid to the y-axis. That's x bar. R equals x bar, which is my divided by the area. According to the shell method, the volume is pi times the integral from 0 and 0 from a to b of x. No, it isn't. It's 2 pi x. That's right. For each rectangle, how do we do this? For each rectangle, I got to draw the picture. Right, we go around like that. So we need 2 pi times a radius. Well, the radius is just the x value here, times a height, which is the top minus the bottom, times the thickness dx. Okay, so that's the volume calculation by the shell method. By Pappus, it says this should be 2 pi times a radius. Well, the radius is x bar times the area, but the area, well, the area is the area. X bar, on the other hand, is calculated as 2 pi times my divided by the area, and then you got to multiply by the area. So sure enough, the volume by the shell method is 2 pi times my. This is Pappus's theorem applied to the shell method, or Pappus's theorem applied to the washer method. Coincidence? I think not.